In this video, I'm going to show you how to find the prime factorization of numbers by using factor trees. So the goal of prime factorization is to express a number as the product of only its prime factors. Remember that a prime number is a number that has exactly two factors, one and itself. So some examples of prime numbers might be 2, 3, 5, 7, 11, 13, 17, 19, and so on. Each one of these numbers cannot be split into any other factors other than one in themselves. So let's start out looking at the prime factorization for the number 54. And to do this, we're going to create something called a factor tree. And basically what a factor tree is splitting this number, this entire number 54, into the product of two of its factors. And then we're going to evaluate whether those factors are prime or not, and we're going to continue going. So the first thing I'm going to think of is what two numbers can I multiply together to equal 54? And what jumps into my head is 9 times 6. So I'm going to write the multiplication problem 9 times 6 right underneath those two branches that are coming out of the beginning of my tree there. And I'm going to ask myself, is 9 prime? And 9 is not prime because I can split it into two other factors, in this case 3 times 3. So I'm going to split this up, and I'm going to write down 3 times 3. I'm now going to ask the same question about 6. Is 6 prime? 6 is an even number, so I know it has 2 as a factor, and so that tells me I can split it up into 2 times 3. And now each of those new factors that I have written on my factor tree, I'm going to ask myself if they are prime. Is 3 prime? And the answer is yes, it is, because it has no factors other than 1 in itself. So all the 3's I'm going to circle. And then I'm going to ask myself if 2 is prime, and even though 2 is an even number, it is prime because it has no other factors other than 1 and 2. So I'll circle it as well. So now I have used a factor tree to find the prime numbers, and now I'm going to rewrite those prime numbers. And when I rewrite them, I always write them from least to greatest, and I group any like numbers together. So I'm going to start with the 2 and then multiply it by each of the 3 3's. So I've now expressed the number 54 as the product of its prime factors, and I can check to make sure that this actually is a true statement by working it out one step at a time. 2 times 3 is 6, then I can bring everything else down. 6 times 3 is 18, and 18 times 3 does equal to 54. So let's look at another example. Let's do the number 72. The number 72, and I'm going to split that up again. The first thing that comes into my head is 9 times 8. And then I'm asking myself, are either of those numbers prime? 9 is not, because I already know that it's 3 times 3 from the previous problem. 8 also is not. It's an even number, so I know 2 goes into there, and 2 times 4 is 8. So I'm going to ask myself, are any of these new numbers prime? And we know the 3 is, and we know the 2 is from our last example. 4 is not prime. It's an even number. So I know 2 goes into there, and it goes into there twice. And these last 2's are also prime. So I know I'm done when I have no more branches that can be split up. All of my individual branches here, these individual branches, all of them end in a circled number. There's no numbers coming off of branches that are either not split up or end in a circled prime number. So now I'm ready to rewrite all of my prime factors as a multiplication problem, and I'm going to start with the smallest number. I see 3 2's and 2 3's. That should equal 72. I'm going to check. 2 times 2 is 4. If I bring everything else down, 4 times 2 is 8. 8 times 3 is 24. And 24 times 3 does equal to 72. The prime factorization is usually expressed using exponents. So in this case, this part right here and this part right here, I could have written using exponents. Instead of writing 2 times 2 times 2, it's more efficient for me to write 2 to the third power. And then instead of writing 3 times 3, I could have written 3 to the second power, 3 squared. This right here is the preferred method of expressing your prime factorization. So let's look at another example. Let's say I'm doing the number 120. And for this example, I'm going to purposely do this in two different ways. So I'm going to write 120 on the left and on the right. And while I'm doing this, I'm going to use different starting points. So on the left-hand side, I'm going to start with 12 times 10. But on the right-hand side, I'm going to start with 60 times 2. Both of those are true statements. 12 times 10 does equal to 120, and 60 times 2 does equal to 120. So let's see if we will get the same answer even if we started using different factors. So on the left-hand side, I'm asking myself, is 12 prime? It is not. And is 10 prime? It is also not. On the right-hand side, I'm asking, is 60 prime? It's not, it's even, 2 goes into it. And I'm asking, is 2 prime? And it is, so I'm going to circle it. So on the right-hand side, I've ended one branch already because this branch ends in a circled number. But on the left-hand side, I've just created new branches. So now I'm going to ask myself on the left-hand side, what are 2 factors of 12? And I'm going to think of 4 times 3. And 2 factors of 10, I'm going to think of 2 times 5. On the left-hand side, 2 factors of 60. I think I'm going to do, let's do 30 times 2. So I'm going to go back and ask myself, are any of these prime? Is 4 prime on the left-hand side? It is not because it's even, and 2 goes into it. Is 3 prime? Yes, it is. We know that 2 is prime. And 5 is also prime. Nothing goes into it other than 1 and 5. On the right-hand side, 30 is an even number, so it has a factor of 2. 2 is an even number, but nothing else goes into it, so it is prime. Back to the left-hand side, 2 times 2 equals 4. 2 times 2. And on the right-hand side, 6 times 5 equals 30. On the left-hand side, both of these 2's are prime, so I'm actually done with the whole factor tree on the left-hand side. Everything is now, all my branches are now ending in circled numbers. On the right-hand side, 6 is even, so 2 goes into it, and 5 is prime. And then 2 times 3 equals 6, and both of those are prime. So now both on the left-hand side and the right-hand side, all branches end in circled prime numbers. So I'm ready to rewrite my prime factorizations. On the left-hand side, I see 3 2's, a 3, and a 5. On the right-hand side, I see 1, 2, 3 2's again, a 3, and a 5. So I have exactly the same prime factorizations here. With prime factorization, with using factor trees, it doesn't matter how you start as long as you choose 2 factors of that number to begin with. So even if you don't think of 2 numbers that are the same as somebody else, you'll still end up getting the same solution, the same prime factorization. I can write this using exponents. 2 times 2 times 2 is the same thing as 2 to the third power. And then I just need to make sure I include the rest in my problem. And I can double check to make sure this is true over here. 2 times 2 is 4. Bring everything else down. 4 times 2 is 8. 8 times 3 is 24. And 24 times 5 does equal to 120. I can check that out if I'm not sure, but it does equal to 120. I do want to share one word of caution to you when you're doing this. So let's say I'm trying to find the prime factorization of 36. What you do not want to do is you do not want to split this into 36 times 1. Yes, those are 2 factors of 36, but 1 is neither prime nor composite. So I can't, not only can I not split that 1 up, I also can't circle it. And then I'm just left to splitting 36 up again. So by putting 36 times 1, it didn't help me at all in trying to discover the prime factors of 36. Also, another word of caution is that it's very easy when you do this 6 times 6 and then split both of these up. It's easy to accidentally think of number bonds from addition and put a 3 and a 3 here, but 3 times 3 is not 6. That would be 3 plus 3. So just be very careful when you're doing that. That's why I always write in the multiplication sign in between it to remind myself that I'm looking for multiplication problems. And this would be 3 times 2 in each of these. And then I'd have the 3's and the 2's prime numbers. I would have 2 2's, 2 3's, or 2 squared times 3 squared. 2 times 2 is 4. 4 times this 3 is 12, and 12 times the 3 does equal to 36.